All right, today we are going to try something new, so hopefully you can see my face. Well, maybe not hopefully, but you can see my face as I'm giving the lecture today on derivatives of cosecant, secant, and cotangent. So let's get started. Okay, first of all, we need to remember that cosecant is the same as 1 over sine x. So to find the derivative of cosecant, I really only need to use the quotient rule on the function 1 over sine x. I know the derivative of 1 and I know the derivative of sine x. So I should be able to do this. Remember, the derivative, the quotient rule for derivatives is you take the derivative of the top. So the derivative of 1 is going to be 0 times the bottom, which is sine, minus the top, which is 1, times the derivative of the bottom, which would be cosine, all over the bottom squared. So that would be sine squared x. And if I simplify that, well, 0 times sine is going to be nothing, and 1 times cosine x is going to be 1 cosine x. Don't forget the minus. And on the bottom, you'll have sine squared x. I'd like to write this, if at all possible, without using any fractions. So what I'm going to do is I'm going to separate it into negative cosine x over sine x times 1 over sine x, which is the same thing as negative cotangent x cosecant x. So just to remember, the derivative of cosecant x is negative cotangent x times cosecant x. That's a rule that you might want to write on a note card or something like that. It will be provided in the formula chart, but you kind of don't want to spend your time going back and forth to the formula chart if you don't need to. So that's the first of the 3 rules we're talking about today. The next one is secant, and we're going to handle that exactly the same way. We're going to take the derivative of 1 over cosine x using the quotient rule again. So the derivative of 1 is 0 times the bottom, cosine, minus the top, 1, times the derivative of the bottom, which is negative sine. All of that goes over cosecant squared. So I end up with positive sine x over cosine squared x. And again, I want to write this without using fractions if at all possible. So I'll separate it into sine x over cosine x times 1 over cosine x. So that is just tan x times secant x. All right, that's 2 of the 3. And then the last one is cotangent, and I'm going to do that the same way, solving for or using the quotient rule on cosine x over sine x, which is the same thing as cotangent x. So the derivative of the top is negative sine x times the bottom, which is sine x, minus the top, which is cosine x, times the derivative of the bottom, which is also cosine x, all over the bottom squared, which is sine squared x. So I end up with negative sine squared x minus cosine squared x all over sine squared x. Now please don't think that you can cross out those sine squareds. You can't, because this sine squared is being added or subtracted to something else. So since sine squared x plus cosine squared x is equal to 1 according to a Pythagorean identity, that means that the opposite is also true, which is that negative sine squared x minus cosine squared x is equal to negative 1. And sine squared x can just stay as sine squared x. So the whole thing is equal to negative cosecant squared x. So the derivative of cotangent x is negative cosecant squared x. So those are, like I said before, those are 3 functions that you might want to put on note cards or flashcards or whatever you use to study with. They are in your formula chart, but it's helpful if you have them already memorized so you don't have to spend your time going back and forth to the formula chart. All right, so those are the derivatives for secant, cosecant, and cotangent. So let's just do an example where things are a little more complicated. We're going to find the derivative of y equals the secant of 3x cubed. So remember, you've got to use the chain rule on this. The first thing we're going to do is take the derivative of the outside function, which is secant. Okay, so, and the derivative of secant, if you remember, is tan times secant. Okay, so the first part of this is going to be tan 3x cubed times secant 3x cubed. And then what I have to do is I have to take the derivative of the 3x cubed part of things, and that leaves me with 9x squared, which gets multiplied afterwards. So everything in the chain rule still applies. The only thing that might be a little freaky is that the 3x cubed before you take the derivative of it shows up twice when you're taking the derivative of secant. And the same thing happens when you're taking the derivative of cosecant. That argument, before you get to the next step in the chain rule, that argument is going to show up twice in the first part of the derivative, and then you take the derivative of that argument. All right. All right, now let's do another one where we have y equals the cosecant of 2x all to the 5/2. So using the chain rule again, I will take the derivative of the 5/2 first. So the derivative of something to the 5/2 is 5/2 times that function to an exponent that is 1 less. So that would be 5/2 times the cosecant of 2x to the 3/2. So that takes care of the 5/2 part of things. Then I've got to focus my attention on the derivative of cosecant. The derivative of cosecant is negative cosecant times cotangent. And again, I will have that argument listed twice. So it is negative cosecant 2x times cotangent 2x. And then finally, I take the derivative of the 2x part, which is just 2. There are some things that can be combined here. The 2 times the 5/2 will give me just 5. And then I have a cosecant 2x to the 3/2 times a negative cosecant 2x to the 1. And that gives me cosecant 2x to the 5/2. And I stuck the negative out front. That was kind of smart. And then I've got this cotangent 2x here that doesn't have anything to combine with, so it can still be here. And as long as all of these things are here and simplified as much as possible, or they're in an equivalent form, in other words, they're in a function that would be graphed exactly the same, the graphs would look exactly the same, then your answer would be still correct. So this is the answer I got, and any variation of that that is an equivalent function would be correct as well. So that is using what they call the reciprocal trigonometric functions and applying them in a chain rule type of way. So obviously tomorrow we're going to have to see what they look like in a product rule and a quotient rule type of way, as well as applications. So if you have any questions, feel free to Facebook me or email me or whatever you're comfortable with, and I will see you tomorrow.